Okay, students, so let's get started with the past papers of O levels in IGCSE physics related to the topic of sound. So let's move on to the first question. A sound wave traveling in air or water contains compression and rarefactions. Okay. Describe an experiment to show that a medium is required to transmit sound waves. You may draw a label diagram if you wish. So this is basically what? This is the bell jar experiment. This is the bell jar experiment that we have studied in the notes. Bell jar experiment. Okay. So let's perform or let's first of all draw the diagram. Let's say this is the bell jar like this, somewhat like this. Pardon me for my drawings. And let's say you have a vacuum pump somewhere here. This is your vacuum pump, and let's label it vacuum pump. And let's say we have a bell attached to it. Let's say we have a bell attached to this. Okay. Now, when the vacuum pump is off, when the pump is off, suction pump, vacuum pump is off, air is inside the bell jar, the bell jar, and you can hear the sound. However, 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 if the pump, if the pump is switched on, if the pump is switched on, what will happen? Air will be removed, or you can say air will start to, air will start to move out of the bell jar, out of the bell jar. This will cause the sound to fade out. This will cause the sound to fade out, and ultimately no sound is heard. And in the end, no sound is heard, you can say. And in the end, no sound is heard. Simple. This tells us that sound requires a medium to travel. When a sound wave passes through air or water, the molecules of air or water move. Okay. Describe the motion of the molecules due to the sound waves. Okay. How do the molecules move due to the sound wave? The molecules vibrate. The molecules vibrate parallel to the motion of wave travel. Simple as that. Molecules vibrate parallel to the motion of wave travel. Simple as that. And if you're a further good student, what you can do, molecules vibrate back and forth. You can do one thing, molecules vibrate back and forth or backwards and forwards. Oh, let's make this towards here, backwards and forwards, parallel to the motion of the wave travel. Simple. State what is meant by a rarefaction. A point where molecules are at the lowest pressure, where molecules are furthest apart, or you can say a point where molecules are at lowest pressure, minimum pressure, anything works here. Let's further move ahead to the next question. No, same question. Figure 4.1 shows a dolphin. Okay, this is a dolphin, a really, really cute dolphin. The range of the audible sound frequencies for the dolphin is this to this. The speed of sound is this. Calculate the smallest wavelengths of sound in water that the dolphin can hear. Okay, we have to calculate the smallest wavelength. That means we will take the highest frequency. That means we will take the highest frequency. This is your velocity. V is equals to F lambda. V is 1500. Okay. What is your F? 140 thousand, and lambda is here. 1500 divided by 140,000 is equals to your lambda. Let's calculate your lambda. 1500 divided by 14000. This comes out to be what? 0.011 meters is your lambda. Simple. Let's move on to the next question. Figure 4.1 shows a wave on a rope and figure 4.2 shows a wave on a spring. Okay. Both waves are moving in the direction shown by the arrows. Okay. State the name of each of the two types of wave shown. What is figure 4.1? A transverse wave. A transverse wave. What is figure 4.2? A longitudinal wave. Longitudinal wave. Okay. On figure 4.1, draw a wave which has a smaller frequency than the wave shown. We have to draw a wave that has a smaller frequency than this. If you have a smaller frequency than this, what will happen? Your time period will increase like this. If you have a smaller frequency, the time taken to complete one wave will increase. That's what I have done here. Describe the movement of point X on the spring in figure 4.2 as the wave passes. How will point X move? Backwards and forwards. Backwards and forwards. Backwards and forwards. Parallel to what? Parallel to the direction of wave travel. To the direction of wave travel. Let's further move ahead. Table 4.1 shows some sentences that a student writes about waves. His teacher places a ring around each mistake. Okay. Write a suitable correction for each mistake in table 4.1. One has been done for you. Thank you, examiner. Sound with a higher pitch has a higher frequency. Okay. X rays are used for prenatal scanning. No, ultrasounds are used. In the electromagnetic spectrum, microwaves have the highest frequency. No, gamma rays have the highest frequency. Gamma rays have the highest frequency. Let's move on to the next question. In a demonstration, a teacher uses a loud ticking clock, two hollow tubes A and B, a barrier, and a smooth surface. The clock is used as a source of sound. Okay. Figure 4.1 shows tube A and the clock. Okay. Both fixed in position on the left of the barrier. Okay. Sound from the ticking clock passes along tube A and is incident on the smooth surface. So basically, sound is passing like this along the tube. Okay, okay, okay. A student listens to the sound passing along tube B, which is on the right of the barrier. Okay. On figure 4.1, draw tube B in the position where the sound heard by the student is loudest. So, where will you hear the loudest sound? Where the complete reflection is happening. Angle of incidence must be equal to angle of reflection. Somewhere here should be your tube be placed. So, let's place the tube here. Let's make the tube here. I think we have to draw the tube, right? Yeah. So let's draw tube B here. This is your tube B. Okay. Explain your answer in one. So what could be the explanation here? Loudest sound occurs at the Reflection or loudest sound occurs due to reflection, due to, due to reflection, and we placed tube B at a point, at a point where angle of incidence I equals to what? Angle of reflection R. Angle of incidence I equals to the angle of reflection R. Simple as that. Let's further move ahead. The speed of sound is this. State a typical value for the speed of sound in solids. So, as far as I am concerned, I like to write 2500 ms minus 1 as my typical value of sound in solid. State what is meant by ultrasound. Ultrasounds are any sound wave having a frequency greater than what? Greater than greater than 20,000 hertz. Describe what happens to ultrasound wave as they meet the boundary between two different materials. Some ultrasounds are transmitted. Some ultrasounds are transmitted and others get what? And others or remaining others get reflected or you can say absorbed. Others get reflected or you can say absorbed. Simple as that. Let's move ahead. To produce the image of an unborn child, an ultrasound emitter and receiver are placed close together on the mother skin. Okay. So basically, you have to form an image of an unborn child. This is an ultrasound emitter, and this is an ultrasound receiver. This is an emitter, this is a receiver. Ultrasounds will be emitted like this, they will reflect the body, and they will be received like this. Let's draw it like this. Yeah, somewhat like this. Let's say this is the newborn baby. Okay. Pulse A is emitted and pulse B is the first pulse that returns from the unborn child. This is pulse A, this is pulse B. Okay. What is the time between pulse A and pulse B? The time taken between pulse A and pulse B is what? 0.03 seconds. Okay. Because this is what? 0.05. This is 0.02. The time between them is 0.03 seconds. The speed of sound is this. Calculate the distance between the emitter and the child. We have to calculate the distance d. How will we do that? First of all, let's calculate the total distance. Total distance is equals to what? Speed. That is 1500 into the time, that is 0.03. 1500 into 0.03. This comes out to be what? 45. The total distance traveled by the ultrasound is 45 meter. But what is the total distance? This thing plus this thing. We only need half the distance. So what will we do? 45 divided by 2. This comes out to be 22.5 meters is your answer. The speed of sound in human tissue is close to the speed of sound in water. Okay. Suggest values for the speed of sound in gases and solids. For solids, I prefer to suggest a value of 350 ms minus 1, and for solids I prefer to suggest a value of 2500 ms minus 1. Let's further move ahead. Figure 9.2 shows X-ray image of a hand. Okay. An X-ray detector is placed just below the hand. An image of the bones and human tissue around the bones is formed on a screen by the detector. Okay. So this is a scanned copy, so it might not be visible, but this entire region is black and the inner region of the hand is white. Okay. All these bones, or let me do it like this. Although this will give out the answer, but all these bones are white because this is a scanned copy, so you might not see it. White is bone, black is flesh. Okay. Describe what happens to X rays to produce the image. What should happen to X rays to produce this image? Okay, what will happen? So, the X rays, the X rays are are blocked by the bones, by the bones. Hence, they produce a white image. Hence, they produce a white image. However, however, X-rays pass through what? Pass through the flesh, producing what? Producing black image. Black image. Simple as that. Let's further move ahead. The wavelength of the X-ray is this, the speed of electromagnetic spectrum is this. You have to calculate frequency. Just apply V is equals to F lambda. We have done this so many times. I'm skipping this for this part. Suggest one reason why X-rays are not used to form an image of an unborn child, because X-rays can cause cancer. X-ray can cause cancer. Can cause cancer. Simple as that. A student reads in a textbook that the speed of sound in air is 300 ms minus 1. Okay. He plans an experiment to check this value. Okay. He asks another student to stand a long distance away in a long open space. Okay. One student has a starting pistol. The pistol, when fired, produces a loud sound and a puff of the smoke at the same instant. Okay. Other pieces of apparatus are needed for this experiment in order to measure the speed of sound. Name two other pieces of apparatus that are needed. Firstly, I cannot see a tape measure or a meter rule to measure the length. So, what will I say? A tape measure, and I also cannot see a stopwatch in the description to measure the time. So, you can write a stopwatch. Okay, describe how all the measurements are made. First of all, measure the distance between the students, the distance between the student holding the pistol, the student, have we given one student has a starting pistol? He asked another student to stand a long distance away. Okay, so measure the distance between the student holding the pistol, holding the pistol, and the student standing a long distance away, standing a long distance away. Okay, what should be your second point? Start the stopwatch. You can say, you can say, start the stopwatch. Start the stopwatch as soon as you, as soon as the student see. Start the stopwatch as soon as the student see what? A puff of smoke. As soon as the students see the puff of smoke. See the puff of smoke. Third key point. Stop the stopwatch as soon as you hear a loud voice. As soon as you hear a loud sound. Is it a loud sound or is it something else? Let me see. As soon as you hear a loud sound. Yeah, that's correct. State a typical value for speed of sound in liquid. The typical value for speed of sound in liquid is 1000 ms minus 1. For solid, I have already told you it is 2500 ms minus 1. Let's move on to question number 6. Figure 6.1 shows a girl standing a few hundred meters in front of a large building. Okay. The girl uses a signal generator and a loudspeaker to send a short pulse of sound towards the building. The sound has a frequency of this. A short time later, the girl hears an echo. State what is meant by the term echo. Reflection of sound. What does echo mean? Reflection of sound. The pitch of the sound is same as that of the original sound, but the echo is not as loud. Loudness decreases. So what would have happened to the amplitude? Amplitude would have decreased. Since the pitch is same, what would have happened to the frequency? Same. The speed of sound is this, the frequency is this. You have to calculate lambda. Again, V is equals to F lambda. V is 330. Frequency was what? 3700. What will your lambda come out to be? 330 divided by 3700 is equals to your lambda. 330 divided by 3700. This comes out to be 0.089. Lambda is 0.089 meters. Simple. Let's move ahead to the next one. Figure 9.1 shows a loudspeaker inside a glass bell jar that contains air. This is the diagram that you can draw in question number 1 as well. This is the same diagram that you can draw in question number 1. The loudspeaker produces a frequency of this. Okay. State what is meant by the frequency of sound. What is meant by the frequency of sound? Number of oscillations per unit time, or number of oscillations in 1 second, either way works. The speed of sound in air is this, the frequency is given, you have to calculate lambda. V is equals to F lambda. 330 divided by the frequency, that is 2200, is equals to your lambda. Your lambda comes out to be what? 2200. Lambda comes out to be 0.15 meters. The sound passes from air into glass, from gas into solid. What will happen to the frequency of sound? It will remain same or unchanged. What will happen to the speed of sound? It decreases. Simple. Let's move on to the next part. Describe how sound is produced by the loudspeaker. How does the loudspeaker produces sound? By back and forth vibration. By back and forth vibration. Simple. This produces sound. How sound is transmitted through air? How is sound transmitted through air? The back and forth. The back and forth. The back and forth. The back and forth vibration. Vibration of loudspeaker causes what? Causes the air molecules to vibrate back and forth. This vibration produces sound and transfers energy as well. Okay, let's move on to part 2. A pump is connected to the tube at the bottom of the glass bell jar. The pump is switched on and it removes the air from the glass bell jar. Explain why the volume of the sound heard outside the glass bell jar decreases. Why the volume of the sound decreases? Because air molecules decrease, and as air molecules decrease, what will happen? Vibration or transfer of energy decreases. Simple as that. This marks the end of the theory past papers of sound. If you have any question, you may ask.